Our last speaker, batting cleanup this evening, is Alan Franzlubers. Dr. Franzlubers is a soil ecologist with USDA Agricultural Research Service stationed in the Department of Crop and Soil Science at NC State University. Dr. Franzlubers has conducted research with soil ecology with both row crops and pastures. His work with the relationship of soil test biological activity and soil nutrient cycling is bringing to question many of our current fertilizer recommendations. Dr. Franzlubers has done extensive research on private farms where he has explored soil nutrient distribution, the relative soil health of pastures, cropland, and adjacent timberland, and the response of tall fescue pastures to added nitrogen during the stockpiling season. So, Alan, welcome to the Producer Pasture Ecology webinar. Are you on? I hope you're on here. I know you are somewhere.
Thank you, Johnny.
There you
yes,
are.
I'm here. Thanks so much. Glad to be here this evening, and glad that everyone can make it. It's getting close to my bedtime, so I hope I don't keep you up past your bedtime. All right. Well, you know, Steve has given us some information on soil health, and of course, the biological basis is only one component of soil health. And I'm going to also be more specific on the biological basis of soil health, in that I'm going to focus on nutrient cycling, whereas the biology plays an important role on the physical attributes of soil, of aggregation, of water infiltration, of compaction or alleviating compaction. And so it can also, and the nutrient cycling is traditionally been a chemical fundamental. And soil fertility is a really strong part of soil health. Soil fertility and plant nutrition encompass the management of essential elements necessary for plant growth, typically to achieve selected management objectives. Well, that actually expresses that it's not just chemical, and that we should be looking at the whole ecosystem in general. So some key elements of soil fertility are that we would want to know about all of the different elements. And those elements are the carbon, hydrogen, and oxygen are the non-mineral macronutrients. And these are essential. This is part of photosynthesis. We need to make, these plants are making carbohydrates from carbon, hydrogen, and oxygen. They're getting the CO2 from the atmosphere and taking water from the soil and combining that with oxygen, and then creating these carbohydrates in plants. This is an essential part of nature, and we need to maximize photosynthetic activity. There are also many of these other elements, such as these primary macronutrients of nitrogen, phosphorus, potassium. These are what we would get from a soil test sample that we would submit to many commercial laboratories. And nitrogen is hugely important in creating proteins and all sorts of molecules in the plants, the nucleic acids, the DNA. And essentially that protein is driving the productive potential of a plant. Phosphorus is an energy element. It's involved in many energy relations, and potassium is a non-structural element that is essentially used as a solute to control water flow and uptake of other elements. And then there are all these other elements that can be important in certain situations. Typically in perennial forage systems, they're maybe not viewed very intensely, because these grasses grasses and legumes tend to have their needs met by the organic cycling in the soil. But they are elements that can be of importance, and certainly in specialty crops they are important. And then there are also some other elements that are not essential, but they could be beneficial to plant growth. So all of this is focused on the chemical nature of soil. And that is what traditional soil testing leads us to, is that we focus on the chemistry. Well, there are some additional considerations also. There may be other elements taken up by these plants. There could be toxic accumulation that can interfere with metabolic function. So too much of an element could be actually detrimental to plant growth. Soil fertility management provides essential elements in sufficient quantities for successful completion of plant metabolic processes and reproductive activities. That is the goal. We want to manage soil fertility to provide the nutrients. But if we manage for soil health, then maybe we're not only applying external nutrients, but we may need to think about recycling. Optimum soil fertility requires adequate quantities of essential elements in a form and location available for plant uptake. This is important because, as Steve mentioned, deep in the profile, you may have actually large amounts of elements that just need to be accessed. And so that location of that element is important. And that could be very true because typically we sample the top 4 to 6 inches for our soil testing calibrations, and we're ignoring elements that are deeper in the profile. And so if we have deep rooting systems, then we should be able to get plants to access them. Historically, prior to industrialization, more than 100 years ago, agricultural production relied on recycling of organic residues, such as manure and plant residues, and as well as biological nitrogen fixation with legumes. So there was this idea that we just needed to, of course, well, it wasn't just, but we had to manage soil so that more of those elements could be recycled. Well, the industrialization process really got us onto this chemical nature, where nitrogen was produced by the Haber-Bosch process starting in the early 1900s, and that led to widespread inorganic nitrogen applications throughout North America and around the world, and that was really ramped up after World War II. And this process is what we know. There are very few of us that are around anymore that knew anything differently. And so now we're trained on this chemical approach, and maybe we can continue this way, but there are alternatives. We don't have to only focus on the chemical nature, but maybe also the biological nature. This graphic here shows that the global cereal production has increased dramatically over the last 60 years. And this is important because we have more people on the planet. And so it needs to balance out. But with that production, we're also seeing a great increase in nitrogen that's applied to our soils and to our environment, and the water that's used for irrigating plants, and the phosphorus that's applied to meet the nutritional requirements of the plants. So nitrogen is the most limiting nutrient to plant growth. And I'm going to use this graphic throughout the presentation to show that without available nitrogen, we have very low yield. And when nitrogen becomes available in sufficient quantity, we can actually achieve our productive potential. However, nitrogen, if we turn the page, nitrogen is also the most common nutrient pollutant. And we see this in this graphic here that around the world, in the coastal regions of industrialized countries, we see high nitrate pollution that is causing hypoxia. This is just a simple fact that nitrogen is a very leaky element, and that when we apply excessive amounts or more than is needed by a plant to meet the maximum production potential, we're going to lose some of that nitrogen. And we're facing this dilemma that we're having so much nitrogen pollution in the environment that we're hurting our potential to produce plants successfully. So this is, again, this idealized response to nitrogen, where we have low relative yield when available nitrogen is low, and we have high relative yield when available nitrogen is high. So the key is, well, how do we define available nitrogen? We can define that available nitrogen through inorganic nitrogen in the surface or deep in the profile, and then various organic nitrogen sources, which we've typically looked at organic matter, soil organic matter, as this long-term stable source of organic nitrogen. But also then we could also look at this biologically active portion of nitrogen, which could feed then the plants as they're growing throughout the season. So we can have sites with low nitrogen availability, and when we apply fertilizer based on the current recommendation system, we would get this high yield response to that nitrogen application, and we would say that, okay, everything is good, the system works. But there are also, and then of course, profitability of the farm would be increasing, and that would be a good thing. We need to apply nutrients when they're needed so that we can get higher productivity. But there are also sites with high nitrogen availability, and it may be from various of these sources here. We don't know which sources. And when we have that high nitrogen availability, we get very low nitrogen fertilizer response. The yield is simply not increased enough to cover the cost of the fertilizer. And so the environmental impact of applying nitrogen based on the current fertilizer paradigm would be that we have this negative environmental impact, and that would not be a good thing. So we want to change our soils to be healthier, to be able to provide a rich source of nitrogen throughout the growing season, and that's through that mineralization of organic matter to an available form that plants can use it. Organic matter is not available, the nitrogen in that organic matter is not available to a plant until a microorganism consumes that organic matter and releases the nitrogen basically as a fecal deposition. It's just an analogy, but as a fecal deposition to that grazing of these organic sources. And so that's the byproduct of this process of organic matter mineralization. And we want to do that in a continuous state, in a slow state, a relatively slow state, so that we do avoid this leakage to the environment. So I'm focusing my research on surface soil inorganic nitrogen and this biologically active nitrogen source. Well, can we predict soil organic nitrogen mineralization? Yes, we can. It is very possible that if we use a simple test, which I call soil test biological activity, an incubation of a re-wetted dried soil that for 3 days at an optimum temperature, sufficient moisture content, we can relate that to net nitrogen mineralization. We determine net nitrogen mineralization in the laboratory after 24 days, and we relate it to soil test biological activity. Organic nitrogen mineralization is a function of the organisms that consume the organic matter. And so there's an association there, and it's relatively predictable based on an equation like this. And with this, we could determine that a soil with relatively modest soil test biological activity could give us roughly approximately 55 pounds of nitrogen per acre. But if we start increasing the biological activity, we can see that there's an increasing potential to supply more and more nitrogen based on that biological activity. And so we could use this as a soil testing paradigm because we're using a dried soil and we're re-wetting it for only a short period of 3 days and determining how much carbon dioxide is evolved by that soil, which then relates to nitrogen mineralization. So how do we measure soil biological activity, and what does it tell us about soil? Well, soil test biological activity is really determined again from this cumulative carbon mineralization over a set period of time. And in this case here, I'm defining the time period as a number of days here, and I'm showing you 0 to 4 inches depth, 4 to 8 inch depth, and 8 to 12 inch depth from a multitude of soils. And these soils often fit this higher activity with near the surface and declining activity with depth. So typically we would like to know the basal soil respiration rate. We want to know if all conditions are optimized in the field, then we want to know how much nitrogen is being mineralized on a daily basis. Well, we can't really do that effectively. It would take us a lot of time to get out in the field, and that would require analyses in the field. We want to take that soil sample and bring it to the laboratory, and we dry the soil so that we give all soils the same conditions, and then we determine this flush of activities, this burst of activity that occurs during the first few days, and then it starts to stabilize thereafter. And we basically put soil into a canning jar, this dry soil, we add the water to its 50% water-filled pore space, and then we seal the jar with an alkali trap in there, and that trap traps the CO2 that is emitted from the soil. The biological activity is producing carbon dioxide, just like I'm spewing out a lot of carbon dioxide now by talking to you. That carbon dioxide is in that canning jar. It's trapped in that alkali solution, and then we determine how much of it has been emitted over time. So we put that soil in there and that alkali trap. And then we basically take that alkali trap out after 3 days, add a color indicator, and then back titrate into the known amount of carbon dioxide that was present in that solution. So I want to bring you to some field results that I think are important to help us understand how the improved soil health can actually lead to greater nutrient cycling. So if we have two situations here where we have no nitrogen fertilizer applied, and we have another part of the field that's had a unit of nitrogen, 100 pounds of nitrogen per acre applied to it. And we see the result that, well, the relative yield, let's say that the relative yield is only 40% with no nitrogen fertilizer, and it's 95% with 100 pounds of nitrogen per acre. We'd want to select the treatment with 100 pounds of nitrogen per acre. It gives us a greater production of our forages so that the animals can actually consume more forage, and of course of higher protein. And that situation would be a normal situation. That's what we would think would happen all the time. But there are also cases where we apply no nitrogen fertilizer compared with 100 pounds of nitrogen, and we essentially get the same relative yield. There's no change. And if that occurred, you might say, well, I did the experiment wrong. It's something just didn't work out right. And that's the way we kind of thought for a long time. But in fact, we've been seeing these kinds of results more than just occasionally. And so something is definitely going on. So why not just use organic carbon to predict nitrogen mineralization? Well, this graphic here shows that, yes, we could see an association between total organic carbon and net nitrogen mineralization, but it's highly scattered. There's not a really tight relationship that occurs. And these data were taken from 3 different farms in 3 different regions of North Carolina. And you see that only you might not see it, but I'm going to explain that 22% of the variation in nitrogen mineralization can be explained by total organic carbon. And total organic carbon is simply the root of soil organic matter. Soil organic matter contains 58% carbon, and so we actually measure carbon in the laboratory and then report as soil organic matter. So soil organic matter could be used in a general sense, but it would not be very predictable, I would say. But if we understand how these data were obtained, I'm showing here now the same exact data that I've just now color coded them to the coastal plain in green, the Piedmont in red, and the Blue Ridge in blue. And so these data are now showing that, well, if I had soil only from the Blue Ridge, I could use total organic carbon to predict nitrogen mineralization. It is possible, but for the soil testing laboratory across the whole state and across the region in our country, it would be difficult to have this relationship be stable. And so there are some reasons why there are differences among these 3 physiographic regions. In the coastal plain, there's the large pool of resistant soil organic matter that can occur following conversion of submerged soil. So there's old organic matter that is simply not very biologically active as compared to the Piedmont. And the difference between the Piedmont and the Blue Ridge is that the sites that were sampled here in the Blue Ridge were from sandy bottomland soils compared with clay upland soils. And so sandy soils tend to have less protective association of nitrogen, and so more of it is mineralized at a faster rate. But if we switch to, rather than total organic carbon on the horizontal axis, to soil test biological activity, all of a sudden, we don't need to know where the soils came from which physiographic region. They all follow the same association. They fall on the same line. We wouldn't have to know where the sample came from. It basically would tell us the biologically active portion of soil, that soil carbon, is actually contributing to nitrogen mineralization. So this leads us to the field trials that were conducted in 2015, 2016, and 2018. Yes, a few years ago already, but basically very relevant and under 3 different yearly conditions and a multitude of sites throughout North Carolina, Virginia, West Virginia, South Carolina, and Georgia. What I need to share with you is that it's not just about the actual yield response, but also about the cost of value conditions of the fertilizer and the forage that could be purchased as hay. So when cost of fertilizer is low and the value of forage is high, we would want to have a low threshold where we want to be able to produce at least 5 pounds of forage per pound of nitrogen. If you're not producing 5 pounds of forage per pound of nitrogen under that condition, then you're losing money. You're spending money on fertilizer that isn't giving you value in actual productive forage that could be harvested as hay or fed as hay or produced in the grassland and consumed by the animals. But we could also be having situations where the nitrogen cost is increasing and that forage value is still the same, and we would need to produce more of that forage to overcome that increased cost of fertilizer. And that could go even further. So all of these are scenarios that you can choose any kind of threshold that is relevant to you today. The cost of fertilizer is important and the value of that forage is important. And those two are needed in synchrony to be able to calculate this threshold of how many pounds of forage are needed to produce to overcome the cost of the fertilizer. So I'm going to give you a few scenarios here where we've tested this. And of course, it was done on 92 fields, but I'm going to just give you a few of these. This happened to be in Person County on a sandy loam soil. It was a 4-year-old Kentucky 31 fescue where it was cut twice annually for hay. And so it's a relatively new pasture that was cut for hay, and it had 70 pounds of nitrogen per acre applied in April 2018, and then this fall period in September of 2018, where we conducted the trial and harvested it in December, January period. These are the conditions of the soil in the top 4 inches, where we had soil test biological activity of 150 parts per million and net nitrogen mineralization of 41 parts per million. That parts per million or milligrams per kilogram can all really be equated in general to 41 pounds of nitrogen per acre. That's essentially the number that you would want to look for. So, but that in current soil testing paradigm, we don't measure that. We might measure 5 pounds of nitrogen per acre in nitrate in the soil. I don't know what the value would be, but it would be relatively low. We don't actually estimate net nitrogen mineralization in most soil testing laboratories. We conducted the trial where we wanted to know what was the forage yield as a function of nitrogen fertilizer rate. So in this case here, we have the 4 rates of 0, 40, 80, and 120 pounds per acre. The dark solid green line is the actual forage yield fitted to these data. And the red line is actually the baseline cost of the nitrogen fertilizer, assuming 5 pounds of forage needed per pound of nitrogen. And that would be the low cost of value threshold. You can see that baseline is increasing over the nitrogen fertilizer rate. The more nitrogen that is applied, you need to produce more and more forage to cover that cost of that nitrogen. So the point where we're going to maximize profitability will be somewhere where the distance between the solid green line and the dashed red line is maximum. And that happens to be at 69 pounds of nitrogen per acre in this scenario here. So in this case here, with relatively low net nitrogen mineralization and relatively low soil test biological activity, the current paradigm of applying approximately 50 to 100 pounds of nitrogen per acre on fall stockpile seems to work. 69 pounds was the result on this field. And so that fit the paradigm very well. Here's another situation in Orange County on a silt loam soil. It's an older tall fescue, and it's a Kentucky 31, and it's rotationally grazed. This is actually at the fall stockpile period where the grass was cut. So you can see that there was plentiful growth of the tall fescue over the fall and into the winter, and we would make that harvest. The biological activity has increased. The net nitrogen mineralization into pounds per acre has nearly doubled from 41 to 85 pounds per acre. And the yield response to the nitrogen fertilizer rate is shown here. Now, all of a sudden, that baseline of that red dotted line is being covered up by the green solid line. But there is some separation there. And the actual economically optimum nitrogen rate was 40 pounds of nitrogen per acre. There actually was some distance between those two lines. It's a minimal distance, but it did show that when applying when applying up to 40 pounds per acre of nitrogen, yield could be optimized, and there could be profitability associated with it. Anything beyond that would be a loss of income. There, you're spending more than you're gaining in forage production. Okay, the third example is in Haywood County on a clay loam soil, a 30-year-old Kentucky 31 fescue, rotationally grazed. There was nitrogen applied in the spring. There's white and red clover present, and the biological activity and the net nitrogen mineralization is increased dramatically. We've almost doubled the net nitrogen mineralization from the previous example. And we can see here that the forage yield response, the solid green line is now below the dashed red line. So the end result would be that in this field situation, we would want to not apply any nitrogen because the soil is already supplying that nitrogen through the mineralization of organic nitrogen in soil. And that was harvested on January 31st, 2019. And the cooperator asked me to come out again because he had not grazed during that winter or spring period. And so a second harvest was taken on the same exact plots that were harvested earlier. And so this was 46 days of regrowth that occurred in this photo here. And this was the original stockpile next to it where it was not touched. And over that 46 days, that's the difference that occurs. Obviously, there's greener grass in the regrowth than in the original stockpile. The yield response didn't change by harvesting it at the second time. There was no need for nitrogen fertilizer. So they told us biological activity again was high, the net nitrogen mineralization was high, and there's this recycling of nitrogen that occurs. I want to synthesize across the sites and show you that this is the statistical distribution of soil test biological activity in corn as well as in tall fescue trials. What you might want to notice here is that the biological activity tends to be greater under tall fescue than under other trials that were under corn production. And so there's a difference in a perennial pasture situation compared to an annual cropping situation. These are categorized into very low, low, medium, high, and very high categories. And this basically is the result of this simplification by averaging these 5 categories. And we can see that this curve that is produced from these data on fall stockpile tall fescue matches very similar the idealized nitrogen yield response. And so we do see that there's this great potential that increasing biological activity leads to greater nitrogen mineralization potential. And again, just to reiterate, this is the situation that we want to be familiar with. If there's a need for nitrogen, we need to apply it. If there's no need for nitrogen, then we need to be informed why there's not a need for nitrogen, and then we shouldn't be applying that additional nitrogen. Just pointing out here, and it's a little bit complicated graph, but basically in all situations, there's an increase in crude protein with any application of 100 pounds of nitrogen per acre. It does increase the quality of the forage, but not necessarily the total production. And in this case, the average crude protein without nitrogen was 11.4%. Typically good enough for most beef cow herds that are available. So across these sites, the nitrogen factor could be simulated here with this low cost of value threshold of 5 pounds per forage per pound of nitrogen, or increasing to 10 pounds of forage per pound of nitrogen. And these are the categories that would be there. And basically, if biological activity is low, we need to fertilize to match the actual crude protein expected in the forage. But if the biological activity is high, that fertilizer, that external input, can simply be reduced considerably, saving producers money and as well as protecting the environment. Okay, well, this was all summarized in a recent paper, and just to share that this is a somewhat accepted approach, although there are in place. We have information. So standard nitrogen fertilizer recommendations do not account for management-induced variation in mineralizable nitrogen, but they should. Soil test biological activity is strongly associated with mineralizable soil nitrogen, and that is a key point that comes out of this research and that you can use as a producer to identify where labs might be using this biological activity approach. And nitrogen fertilizer recommendations can be adjusted for field-specific level of soil test biological activity. This is important because we don't treat all fields the same way. We actually need to know what are the conditions of the soil. To summarize, pastures are an ecological system that evolve over time with high degree of nutrient conservation. So we can take advantage of that situation because there's a buildup of organic matter, and that biological component is very important in cycling. Soil test biological activity is the simple, rapid, and robust indicator of soil nitrogen availability. It is not the actual nitrogen availability. It's a process of association. We're indicating that there's high nitrogen availability when there's high biological activity. And balancing of productivity, environmental quality, and profitability of pasture systems can be achieved with alternative soil testing. Thank you for your attention. And Johnny, I apologize for going over.
Actually, you're right on time, Alan. I think we started about 5 minutes late, so you're in good shape. So appreciate that, and really always enjoy hearing Alan present information. And I think the biggest thing that I like is that he challenges the status quo and, gets us to thinking about a return on investment, and we really need to think about that on any of our inputs, not just nitrogen or fertility. So Alan, thanks for bringing that out this evening.